Have you ever stared at a secret message, a string of jumbled letters, and thought, there is no way anyone could ever crack this? Well, today, we're going to pull back the curtain on a classic code-breaking technique that reveals a huge weakness in ciphers that seemed, at one point, totally unbreakable.
So here's the big question, right? In a substitution cipher, every letter in a message gets swapped for a different one. The key that tells you which letter becomes which is supposed to be top secret. So if you don't have the key, how on earth could you possibly read the secret message? It seems impossible.
Well, the secret isn't actually about attacking the cipher head-on. The real vulnerability, the secret weakness, lies in something much more fundamental. It lies in the language of the message itself.
And this, right here, is the absolute core idea that makes the whole thing possible. Languages are not random. Not at all. Every single language we speak, whether it's English or Spanish or French, it follows these predictable patterns. And that structure, that's the fatal flaw.
Think of it like this. Every language has its own unique fingerprint. For example, if you take any big chunk of English text, the letter E is going to show up way more than any other letter. It's just a fact. Then you have letters like T and A, which are also super common. This consistent, predictable pattern is what lets you identify a language even when it's all scrambled up in a cipher.
Okay, so how does a codebreaker actually use this knowledge? Well, the process is kind of like being a detective. You're not smashing down doors, you're carefully, patiently following a trail of clues.
The whole attack is very methodical. First, you just count. You tally up how many times every single symbol appears in the secret message. Step 2, you compare those counts to what you already know about the language. So you look for the most common symbol. Step 3, you make an educated guess. That symbol that appears the most, it's probably an E. And finally, you just repeat. Once you're pretty sure you found E, you can start looking for common 3-letter words like the, and piece by piece, the rest of the message starts to come into focus.
And here's the really crucial part. By analyzing these statistical patterns, the attacker completely bypasses the need for the secret key. They don't need it. It's like they're not trying to pick the lock, they're just studying the shape of the keyhole so carefully that they can figure out the exact shape of the key.
So let's talk about that first crucial step. How does a codebreaker even begin? How do you make that first educated guess with any confidence? Let's see how it works in practice.
Often, the very first foot in the door is what's known as the E clue. It's simple. If you're looking at your encrypted text and one symbol just keeps popping up way more than anything else, it is a very safe bet that it's standing in for the letter E. And once you have that, you have a starting point to unravel everything else.
But okay, I know what you're thinking. What if you're wrong? What if the most common symbol isn't E in this particular message? Did you just fail?
Not at all, because the whole process is self-correcting. Let's say you make a wrong guess. You swap in an E where it doesn't belong. You'll pretty quickly start to form words that are just complete nonsense. You'll see patterns that just don't exist in English, and that's your signal that you made a mistake. So you just backtrack, erase that guess, and try something else. It's really just a process of trial and error, a lot like solving a Sudoku or a crossword puzzle.
This whole iterative process really shines a huge spotlight on the fundamental reason these types of ciphers just aren't secure. So, what is that fatal flaw? It all boils down to the single powerful idea: patterns leak information. It doesn't matter how cleverly you scramble the letters, as long as the underlying structure, the patterns of the language are still there, you are leaving a trail of breadcrumbs for an attacker to follow.
Just take a look at this example. We have the plain text, the quick brown fox, and below it, the ciphertext. Now, yeah, the letters are all different, but look closer. The structure is identical. A 3-letter word is still a 3-letter word. A 5-letter word is still a 5-letter word. You see? The encryption hides the letters, but it completely fails to hide the structure of the language underneath.
Now, it's really important to note that this method isn't some magic bullet. Frequency analysis works best on longer messages where all those statistical patterns have room to show up. A really short message, something like "attack at dawn," is way harder to crack this way. And this is the big one, this technique is totally useless against modern encryption. Modern systems are specifically designed to destroy these patterns, to make the ciphertext look like complete and utter random noise, erasing that language fingerprint entirely.
Honestly, the discovery and refinement of frequency analysis basically made these simple substitution ciphers obsolete. It was a huge turning point in the history of cryptography, and it forced people to come up with much more sophisticated ways to hide information.
So let's just do a quick recap. What are the big takeaways here? First, frequency analysis works by exploiting the predictable, non-random patterns of language. Second, it lets you break these simple ciphers without ever needing the secret key. And third, this very weakness is what drove the invention of the more complex and secure ciphers that we rely on every single day.
So, if just replacing letters one for one is a dead end, what's the alternative? Well, in our next explainer, we're going to dig into a totally different approach. What happens when you don't replace the letters at all, but instead you just shuffle them?